All right, are you ready? You're still in your relaxation mode? I'm still in my relaxation mode. I hope that permeates to you. So let's get back and review what we're talking about in terms of the action potential. Let's check out this animation on neuron physiology.
Action potentials propagate in a continuous fashion in unmyelinated axons. Once an action potential is generated in the initial segment of the axon, it propagates the entire length of the axon. Recall that a threshold stimulus causes voltage-gated sodium channels to open. The influx of sodium ions generates an action potential. It also establishes a depolarizing current that flows to the next segment and brings it to threshold. Voltage-gated sodium channels open, regenerating the action potential in this segment of the axon. Current flows from this segment and depolarizes the next segment to threshold, thus regenerating the action potential yet again. In this way, regeneration continues in one direction all the way down to the axon terminals. The basis for unidirectional propagation is revealed when we take a closer look. By the end of the depolarization phase of the action potential, all voltage-gated sodium channels inactivate and voltage-gated potassium channels open. These two events render this segment of the axon temporarily insensitive or refractory to another depolarizing stimulus. However, voltage-gated sodium channels in the downstream segment are closed and receptive to a depolarizing stimulus. Thus, propagation occurs sequentially down the axon to the axon terminals. In myelinated axons, action potential propagation is a bit different. Here they propagate in a saltatory or leaping fashion. The myelin sheath consists of multiple layers of tightly wrapped glial cell membrane. But this sheath is not a continuous one. Exposed areas of axonal membrane, known as nodes of Ranvier, occur at discrete intervals. Voltage-gated sodium channels are abundant in the nodes, but largely absent between nodes. So, action potentials are regenerated at each node, not in areas covered by the myelin sheath. However, the myelin sheath does provide the insulation necessary for the rapid spread of depolarizing current. And the sooner the nodes reach threshold, the faster action potentials propagate along the axon. Saltatory conduction is extremely fast. Velocities often exceed 100 meters per second. In contrast, continuous conduction is fairly slow. Velocities rarely exceed 2 meters per second. Nevertheless, both continuous and saltatory conduction propagate action potentials over varying distances because action potentials regenerate along the way. Summary: propagation of an action potential. Once generated, the action potential propagates the entire length of the axon without decrement.
So that's one key aspect of that, right? So when you look at it, again, the myelinated axons have that signal traveling much further because we only have to regenerate and open up those channels at those nodes of Ranvier. So imagine if you were going downstairs and you wanted to get down there very fast, you might jump, right? Every third step or something like that, as opposed to taking every single step like we do in an unmyelinated one, right? You get down there much faster. So that's why they call it saltatory conduction. Saltaire, like a ballet move, has to do with leaping or jumping, and that's where that term comes from. Okay, so regardless though, when we see that, right, when you saw the response when it was occurring in all those different nodes, you saw that action potential was the same height every single time. So even when we're stimulating the cell more or less, we're not going to get bigger action potentials and smaller action potentials. You'll just see a change in frequency. So like we see in this graph here, when we see a stimulus, and it has to be above threshold, right? When we see a stimulus of a certain duration, you might get a certain number of action potentials. And when you see a stronger stimulus, either stronger or longer stimulus, you're going to get more action potentials. But notice, right, those action potentials are the same each and every time, right? Starts out at -70 up to +30 and down to about, -90 or so like that, and then comes back again. Same thing every time. So we see the frequency changing in the action potentials according to a stronger stimulus. So it's always going to be frequency as opposed to changes in size or amplitude. Okay, we also said that the action potentials can only go one way, because after it passes through a section, just like a section of people in the stadium, they're tired, they got up, they got down, they don't want to do it again for a while until it comes back around, right? So they go into what's called a refractory period, and there's what's called an absolute, and then there's a relative refractory period. So for instance, those people in the stadium, if you hit them up right away and you're like, come on, stand up again, they're like, forget it, I don't care what you say, I'm not doing it, I'm not standing up again, I just sat down, right? Absolutely not. Meanwhile, after a period of time, they're not fully recovered, and if somebody gets really jazzed and like, come on, let's do it again, they might, with a stronger stimulus, they might be able to generate their action potential or kind of stand up and sit down again. So absolute, no way. Relative, okay, if you really get me going, really get me excited, then we can generate another action potential. But like we said, the threshold is elevated, so you have to get a strong stimulus, right? So refractory period applies in various ways. We'll talk about it in Bio 202 as well. But it's this period of time when you cannot respond, or after a stronger stimulus, you might be able to respond. Okay, so the absolute refractory period is going to be this time like we see across here, when our action potential is being generated. Once we go into repolarization, we enter the relative refractory period, where if we stimulated it more, you might be able to get it to generate another action potential quickly. All right, so how fast are these impulses going down? So the impulses, action potentials, are only occurring in our axons, right? And the speed or the velocity at which depends on two factors. Number one, the axonal diameter. So if we have a bigger diameter, like a big neuron, then they tend to conduct faster. And degree of myelination, right? Because we can hop down it. If we have a lot of myelination, as opposed to maybe just a little bit at the beginning, then we can hop down there much faster. So continuous in an unmyelinated one is slow, but in a myelinated one where we can hop and jump, then saltatory conduction gets it down there much faster as well. So that's the difference between the two types that we see right here. Let's take a look at that.
As we discuss the propagation of an action potential, we will first discuss propagation in an unmyelinated axon, and later contrast this with propagation in a myelinated or insulated axon. In the multipolar neurons shown here, action potentials begin at the axon hillock, a region of the neuronal membrane at the beginning of the axon. Depolarization of the axon hillock to threshold generates an action potential. That action potential travels or propagates like a wave down the length of the axon from upstream regions near the axon hillock to downstream regions near the axon terminals. In an unmyelinated axon, action potentials propagate in a continuous fashion. To understand how this occurs, we'll focus on a zoomed-in view of a section of the axon. We'll monitor the membrane potential with a voltmeter at a single point and watch as the action potential passes through that point. At time 0, the action potential is in an upstream region of the axon. The influx of sodium ions in this region causes positive ions to move within the axon. These movements of charge are known as local currents, and they depolarize downstream regions of membrane to threshold. This generates an action potential in this adjacent section of membrane a little further down the axon. Note, however, that our section of the axon is still at the resting membrane potential at this point. 2 milliseconds later, the action potential arrives in our section of axon. Local currents from upstream regions have depolarized this region to threshold, opening voltage-gated sodium channels. The resulting influx of sodium ions has depolarized this section of axon, which the voltmeter shows as being at the peak of its action potential. The depolarization of this segment also sets up local currents that depolarize adjacent downstream regions to threshold. These local currents do not generate action potentials in the upstream region. The upstream region has just experienced an action potential, so its sodium channels are largely inactivated and cannot open. This means that the action potential only propagates in the downstream direction, towards voltage-gated sodium channels that are closed and ready to open. At approximately 4 milliseconds, an action potential has passed through the segment monitored by the voltmeter, and sodium has begun to diffuse into the cell through open voltage-gated channels in the next adjacent segment due to local current flow, repeating the cycle. As local currents flow down the axon, the action potential continues to move forward away from the axon hillock, since the voltage-gated sodium channels are inactivated in the previous segment. This period of time, when voltage-gated sodium channels are inactivated, is called the refractory period. In unmyelinated axons, this entire process is called continuous conduction and repeats at all segments of the axonal membrane, recreating or propagating the action potential over and over, something like a domino effect. Action potential propagation in a myelinated axon is quite different. In a myelinated axon, the myelin sheath acts as an insulator and prevents ion exchange in any axonal segment where it occurs. Notice that the myelin sheath does not cover the entire surface of the axon. Between long myelinated regions, about 1 millimeter in length, are short, exposed areas of membrane called nodes of Ranvier. In myelinated axons, action potential regeneration occurs only at the nodes where the voltage-gated sodium channels occur. Once again, the action potential develops at the axon hillock due to an influx of sodium ions, and the action potential propagates down the axon. The myelin sheath permits local currents to quickly flow long distances between nodes without dissipating. This quickly depolarizes the first node to threshold and generates another action potential even though it's far from the axon hillock. This leaping of the action potential continues from node to node and is called saltatory conduction. Like continuous conduction, saltatory conduction also moves down the axon away from the cell body, since the previous section is in a refractory period, but the propagation speed is much faster. To summarize, in both unmyelinated and myelinated axons, action potentials are initiated at the axon hillock and propagate in a single direction, regenerating without decrement along the axon's length. Local currents at the leading edge of the action potential depolarize downstream regions, which leads to the activation of voltage-gated sodium channels and the regeneration of the action potential. In unmyelinated axons, this is a relatively slow and continuous process and is typically found in neurons serving internal organs where slower responses are not a handicap. In myelinated axons, this is a fast and saltatory process where action potential regeneration occurs only at the nodes between sections of myelin and is found in neural pathways that require more speed, like in nerves that control skeletal muscles.
And there you go. See? So, important information to be able to contrast how an action potential works and then be able to compare between unmyelinated and myelinated axons as well. Lots of different comparisons. That's why we're kind of doing this in a stepwise process, kind of recapping each of our steps of learning along the way. Now, sometimes you may hear about different types of diseases and disorders that actually affect this process as well. So, for instance, multiple sclerosis, you hear about MS, right? This is an autoimmune disease, which means that your body has lost the ability to detect what is foreign, and now it's attacking our own cells. And so the myelin sheaths in the central nervous system are destroyed. So what are the cells that are going to be affected here? What creates the myelin sheaths in the central nervous system? Neuroglia cell that's called a oligodendrocyte. So what happens then is we get these hardened lesions that are called scleroses. That's where multiple sclerosis comes from. And so what happens is, right, we're going to decrease the amount of myelin involved, so we're going to slow down the impulse, and it may even stop or cease the impulse. So that way, if we can't get these neurons to respond, then there's going to be all kinds of issues in terms of, controlling muscles and things like that. Okay. Lastly, what we find is when we talk about these different nerves and nerve fibers and conducting impulses and things like that, we have different groups of them, different categories based on size and based on myelination, right? So group A fibers have the largest diameter, they're the biggest, and they are myelinated ones. And so these ones, like going down to the muscles so that we can get them to move quickly, etc., those are going to be the fastest. They can be almost 300 miles an hour, which makes sense, right? You're going to be able to do these things. You think it's like instantaneous, but you have to decide to do it, sensory information coming in, make a decision about it, motor information coming out, and then have it happen, right? So it has to be quick. Group B fibers are kind of like mid-grade, right? Intermediate in terms of diameter, lightly myelinated. They transmit about a tenth as fast, 30 miles an hour, which is still super fast, right? 15 meters per second, you are only like 2 meters maybe. Group C fibers are the smallest ones. They're unmyelinated, and they go about 2 miles an hour, like a good walk. But these ones are going to be like within like organs, like within the brain, right? The gray matter processing and things like that. Relatively small neurons, not going too far. So we have different categories. So, like we were talking about, things that can affect this movement of signals can certainly affect all kinds of different aspects of the body. And so we saw diseases or disorders that can do it, but there's also, for instance, anesthetics, right? Novocaine, things like that. They're blocking these fibers, like sensory fibers that's going to relay the information to the brain. They're still drilling that tooth and, jabbing you in the gum and stuff like that, but you don't get the feeling because those sensory nerve fibers are not transmitting their impulses. So blocking our sodium channels, no action potential, no relay up to the brain. Go ahead, I'll drool all day, but I'm not going to feel it, right? Cold temperature and even continuous pressure also can disrupt the cellular activities, right? Get them to stop their normal cellular activities. So if we don't have enough oxygen, etc., then our neurons are going to be affected, just like our muscles could be affected. And so then those neurons are also not going to be sending impulses. That's how you can get a limb going numb or something like that when you talk about something falling asleep. Okay, so that takes us through neuronal physiology and neural tissue. So lots of information there down to the cellular level. Spend time with it, review those short animations and videos, but know that you have to know how these cells receive signals and send signals in order to understand how the system itself works. So our next section, we're going to scale up from there, and we're going to start talking about different aspects of the central and the peripheral nervous system and what they do.